Functionalist system thinking can deal with technical and probabilistic complexity much more effectively than it can deal with purposive complexity, because purposive complexity is really not important. Hence, the boundaries of Z1 extend further along the technical and the probabilistic axes, which means that we can use all the quantitative techniques and mathematical models that can handle technical complexity and also probabilistic complexity if, for example, the probability distributions are known. Functionally, system thinking can deal, all right. Interpretive system thinking, on the other hand, can deal with technical and probabilistic complexity to a lesser extent than functionalist. Whereas it can deal with purposive complexity to a greater extent than functionalist system thinking. Therefore, the boundaries of Z2 extend further along the purposive axis, but not along the technical and probabilistic axis compared to the case of functionalist approach. Finally, the emancipatory approach is suitable for problem situations lying far out on the horizontal, the purposive axis. These are situations involving irreconcilable conflict. Now, emancipation, these blue colored comments are definitions for you usually. Emancipation means freedom from legal, social, or political restrictions, okay? So emancipatory systems thinking is concerned with emancipation from restrictions. These restrictions are a result of having a multitude of different and conflicting purposes. Okay? Such situations can also involve high levels of uncertainty and a certain level of technical complexity, but these are of secondary importance. Not secondary importance, but we have to deal primarily with conflict in these situations. Purposive complexity is so dominant that the priority in emancipatory thinking is on conflict rather than on technical and probabilistic aspects. That is why Z3 is drawn smaller. All right? I think now all this is clear. Now let us discuss each one of these approaches in a little bit more detail. What do you mean by the functionalist systems approach? Well, there are many points that we can make. The first one is that subject-object duality can be assumed to hold in general. Now, we have argued that subject-object duality is the assumption of Newtonian science, which does not really hold today. But in the functionalist approach, it is as if we can assume this duality holds. All right? And the systems that we are concerned with in this sort of inquiry can be regarded more as ontological constructs, out there constructs. Different points of view about the system are allowed. There can be many objectives, but they are reconcilable. Therefore, there is a common goal, a unitary, like minimization of costs or maximization of profits or something like that, can be agreed upon. The question is not what to do. We know what to do. We have to minimize costs. The question is how to do it. Here, then, you can use all the mathematical techniques that you are learning. All the hard arsenal, let's say, the hard equipment of OR, which relies on optimization and stochastic processes and statistics, can be used efficiently in this sort of situation. Because we are trying to discover we know we have decided what to do, we are just trying to discover how to do it. So it has widespread applicability. It can be applied in situations like which involve high technical complexity and some manageable uncertainty. From manageable, you see, uncertainty is a term that can be used to mean different things. It has different meanings. normally, we differentiate uncertainty from risk sometimes. Do you know this distinction of risk and uncertainty? When we talk about risk, what do we mean? What is available? Decision-making under risk and versus decision-making. Well, there are decision-making courses. We have a decision theory course as a technical elective. Maybe you can take it up next year and learn more about these. Risk means there is probability, but the distributions are known. Uncertainty often means the distributions are not available, the probability. You know the significance of a probability distribution, I hope. Huh? Do you understand the significance of a probability distribution? If we have a probability distribution, we know everything about the probability system. We can compute all sorts of probabilities. We can compute all sorts of central measures like means, variances, modes, medians, standard variations, coefficients of variations, everything, all the moments can be calculated. All probabilities of all sorts of events can be defined and calculated. This is the F function, the capital F, the distribution function, which is the probability that the random variable x is less than or equal to, let's say, t. It's determined as f of t. If this distribution function is not available, then we are in difficulty. Then, for example, in statistics, can you implement estimation if you don't know the distribution? Can you test hypotheses, for example, if the distribution is unknown? Or what do we call those methods used for estimation, hypothesis testing, etc., if the distributions are not known? What do we call those methods? They are called non-parametric methods, non-parametric statistics. That's an area where the distributions are not available and you are in difficulty. If the distributions are available, then you can be very precise about the level of probability. So manageable uncertainty usually means that the distributions are available. So the functional systems approach can be is used in hardware. It's used in what we call systems engineering, systems analysis, cybernetics, etc. Most of these related but slightly different approaches use the functionalist approach. All the courses that you have taken in OR and other technical courses are written from the point of view of the functionalist approach. We assume there is a clear objective, etc. The interpretive approach regards systems more as epistemological constructs rather than ontological. Usually there are multiple objectives that are not necessarily irreconcilable. So we can probably reconcile these, not necessarily irreconcilable. But in the functionalist approach, we know that they are reconcilable. Hence the question is more about what to do and less about how to do it. So the functionalist focus is on how to do things. The focus is on what? On how to do things. So the focus must be on which E? The 3 E's? Efficiency. In the functionalist approach, the focus must be on efficiency. In the interpretive approach, the focus must be on what to do. So it must be on. Are these concepts not clear? We have discussed these so much. Doing things right and doing the right thing, efficiency, effectiveness. Didn't you learn these things? I mean, if these ideas are uncertain, still fuzzy, then you are in trouble. You will have the first midterm examination on the 28th. Well, the only midterm examination, actually, on the 28th. So, some weeks from now. And please make sure that you learn all these things. Huh? You'll be in difficulty otherwise. So the technical complexity and uncertainty are less relevant and are not handled routinely. Lütfen. The goal of the interpretive approach is to learn about the system rather than solve optimization problems, to learn about it. It doesn't mean, of course, that you don't construct optimization models. You can construct all those things, but they are tools for learning about the system so that shared commitment to action becomes possible. It means that people can come together and decide on what action to take. This is the goal of, actually, the modern understanding of operations research or industrial engineering is this: to be able to produce decision to act together, even though the decision makers, all the stakeholders, might have different objectives, different concerns, etc. This is actually the purpose, the objective of an organization. People, why do people organize? In order to implement a common goal, right? But in organizations, organizations are purposive systems, as you know, in which we have individuals, goal-seeking individuals having different goals. But still they come together in an organization because there's an overarching, an overall goal also that they would like to serve. So the problem and the success of any organization, of a political party, of a sports club, of a graduates organization, of a manufacturing company, etc., is always being able to come to this sort of result, shared commitment to action. Your profession aims to provide this. This is your job, shared commitment for action to make it possible, even though values may not be shared and objectives are different. Okay? So the interpretive system, this is how you should regard your profession as. Your profession serves this purpose only and only this purpose, if you ask me, in my opinion. Software uses this. Well, this one, emancipatory approach, is the most difficult. Again, epistemological construct. Essentially different conceptualizations of the system by stakeholders. Each stakeholder sees the system completely differently from the others. Political systems, actually, fall into this category. Political problems usually are of this type. So the boundaries are subject to disagreement. Objectives, as I said, are not reconcilable. All the question is about what to do, not how to do it at all. Full emancipation is often not possible, since positions of power will not be given up willingly. It is like, for example, the conflict between workers and capitalists. These conflicts cannot disappear at all. They are always there. So what happens is that the powerful parties, the parts which hold the power, are able to exercise the power on the others, and full emancipation from these restrictions will not be possible. This is an area that OR has been addressing in several places, but it's a very difficult area, as you can see. Coercion may leave no possibility except conflict. Coercion, we have discussed this. Coercion is applying force on unwilling parties, on other parties. Passive resistance, disobedience, etc. May be the only courses of action left. Now, passive resistance, for example, we are witnessing this in the south of Turkey in the last weeks or so. The population there have started passive resistance, for example. They are sitting now under the police coercion, etc. Disobedience. So technical complexity and uncertainty are much less relevant than conflict in these sort of. So you see, conflicts of this type involving politics, national politics, etc., are within the domain of systems thinking and OR. We are not going to study these very much. These are not addressed in your book also that much. There are several papers and literature in this area that you can explore later if you are interested. Now, let's go to, from these classifications, let us go slowly to hard OR and see how the methodology of hard OR works out. Hard OR and hard systems thinking in general are functionalist approaches. The traditional applications of industrial engineering are often based on this hard functionalist approach. Soft OR and soft systems thinking in general use interpretive and in some cases emancipatory approaches. As I said, only a few emancipatory methodologies have been developed. Applicability is limited since the situations are very complex. Soft approaches are mostly experiential. Experiential means you formulate your approach as you do it, through experience. Not ex ante, not before you start implementation, but as you implement. This is an attribute of soft OR. We try to have our students conduct a soft approach in some years during the history of this course, but the difficulties were too great. I mean, it is easy to find soft OR projects, to formulate soft OR projects. Within the university area, we formulated some problems, but the difficulty is if you are working in groups of 3, there will be maybe 30 groups. These 30 groups will have to go and speak and interact with the owners of the problem 30 times, and nobody can stand repeating this 30 times. So we stopped. And of course, we discovered that in hard OR also, our students are very poorly equipped, so you are going to do a hard OR project. All right. Now, what is hard OR? It can be defined looking at the paradigm of hard OR can be understood by reading these points. The problem has been clearly defined. So in hard OR, the problem is well defined. What does it mean? The objectives of the decision maker are known, and there exist criteria to see when they have been achieved. Even if there are conflicting objectives, trade-offs can be defined. And these trade-offs, for example, can be formulated in an optimization model as constraints, these trade-offs. Alternative courses of action are known as a list of options or as a set of decision variables. The constraints on the decision choices are also known, and the input data is usually assumed to be available somehow. Secondly, the problem is relatively well structured. What does it mean? Meaning that the relationships between the variables are known. System behavior can be captured by mathematics. And the computational effort needed for obtaining a solution is economically feasible. You can obtain a solution. The third attribute is that for the hard OR paradigm is that the problem can be sufficiently well insulated from the wider system. There is a strong separation of the narrow system from the wider system, so that boundary setting is relatively easy to decide. You are not too unsure about what the wider system is and what the narrow system is. Often, optimization is the ideal. We try to optimize whenever possible. The problem is mostly of a technical nature, free of politics, because there is unitary I mean, politics will enter into the problem situation. When does politics enter? What happens when politics enter? I mean, your answer, you have to answer me in terms of what we have learned, not generally. Politics enters when there are a multitude of objectives, not a unitary objective. When the number of objectives increases, that is when you have politics. When you have a single objective, you don't have politics. You just pursue that objective. If there are multiple stakeholders, a consensus can be assumed to be reached, and the decision maker has the power to implement the solution. All these are assumptions of hardware. Now, the methodology of hardware is summarized in the textbook very, very nicely. I like this diagram very much. I mean, you can find chapters, papers, books about the OR methodology, which try to describe this in different ways. This is the best representation or description I have seen. Dellenbach wrote the textbook many, many years ago, its first edition. Then Ömer Kırca discovered it maybe 10 years ago. We tried to use it, but we couldn't use it properly in our courses until we introduced this systems thinking course. When we introduced the course, Dellenbach fortunately wrote the second edition, the edition that you are using now, and it's this diagram from that book. It's very, very nice. They are now working on the third edition. They discovered that we were using their book more than anybody else in the world. So they wrote to me and asked me how they should change the book in the new edition. Okay, I'm hoping that they bring out a new edition. So look at this diagram now. The 3 steps of hardware methodology are indicated by the 3 large ellipses. At the top here we have formulation, then we have modeling, and then implementation. And you can see that there is some overlap among these large ellipses. They are not independent from each other. There is some overlap here, for example, and some overlap over there. And in each of them, there are other steps. For example, formulation or problem scoping. Forget about problem scoping at the moment. That will be clear later on. In the formulation phase of the hardware methodology, what we do is we summarize the problem situation. We are confronted with a problem situation, so we have to learn about it and understand it and summarize. Then identify from that situation a problem to address and describe the relevant systems associated with that problem. An outcome of this step could be, for example, a project proposal. You might write a project proposal. We shall see examples of these, I think, in the textbook. So the implementation of the first step does not necessarily mean that the modeling and the implementation steps will come after automatically. They will come after if the stakeholders decide that the inquiry is going to be useful. Then comes the next phase. This is called modeling. Build a mathematical model. The mathematical model can be built when the narrow system is identified. I have been telling you this. Here it says describe relevant system. So you have identified the narrow system of interest. Then you can construct a mathematical model of that. Find a preferred solution, test the validity and the performance of the solution, analyze the sensitivity of the solution. From this phase, the outcome, what we like to call as deliverables, the deliverable could be a project report. For example, the term project that you are going to conduct will consist of this formulation and modeling, because implementation is obviously not going to be possible. So the project report you are going to submit is this one here. And after that comes the implementation phase, where you plan the implementation, establish control over solution, implement the solution, follow up the solution, etc. So we shall see the details of each of these steps. The important thing to see here is that there are very thick arrows. There is a thick arrow going in this direction. There's another one. So these large arrows, the shaded arrows, linearly follow subsequently one after the other. But then there are other arrows which are going back in broken lines, as you can see. For example, it is possible that after you describe the relevant system, to go back and summarize the problem situation. Similarly, after the sensitivity analysis, you may have to go back to model building, etc. So even after the implementation, you can go back to the problem situation again. So this research cycle goes on most of the time, and it cannot end really. Huh? I mean, do you believe that you can make a list of problems in your workplace when you take a job in a workplace? Is it possible to make a list of all the problems to be solved and then start solving them one by one? You solve the first 5 problems and then eliminate them from your list. And then your job is easier because there are only 3 more problems left. Life doesn't work out like this. As you eliminate problems, new problems have to be added at the bottom of the list. Otherwise, there will be no need to work as IEs. So this loop is always here. The loop is completed by broken lines, implying that it may not occur all the time, and this is true in hardware. Hardware projects may have a definite end. In software, we shall see that it never ends. In software, the cycle is not broken at all. Learning, it's about learning, and it doesn't come to an end. Okay, now more importantly in this diagram is this. You see, here on the right-hand side, we have the abstract world. And on the left-hand side, we have the concrete world. This is the world we know. This is the mental world we have. You see, modeling is closer to the abstract world. What does this mean? It means that your model is a representation of an epistemological system, of a mental system. That's why it is drawn closer to the abstract world. But the formulation and the implementation phases must take place in the real world, in the ontological world. Here you have the epistemological space, and here you have the ontological space, if you can use these terms in this way. And at the bottom, there's an arrow, qualitative, quantitative. You see, as we move to the abstract world, will we be more able to use quantitative analysis, mathematics, etc. As we come back to reality, often mathematics itself on its own will not be sufficient, and you have to make qualitative judgments. All right, so the diagram is very well constructed, pointing out all these aspects. Here you have another output called the solution audit. What does it mean? An audit is like a carnet, is like a report card, a performance evaluation. Audits are evaluations. For example, there are financial audits conducted by accounting firms working on the balance sheet of a company which is a member of the stock market, whose papers are traded in the stock market. So an audit, a solution audit means after the implementation, we try to determine whether our long-term aims have been achieved by this implementation. Huh? Okay. So the figure implies that hard OR is not all hard. Why? Well, you see, this is not hard. Qualitative aspects are in hard OR. The formulation phase, which involves issue and problem structuring, and the implementation phase, which involves human considerations, relate to ontological aspects that are qualitative rather than quantitative, that are messy. Messy. You know, Ekhoff defines a problem situation as a mess. A mess. A problem situation is a mess. A mess is something that you cannot easily understand and separate into coherent parts. Messy. The modeling phase relates to epistemological aspects which accepts quantification. This means that the hard-soft distinction, or in fact the functionalist interpretive distinction, is not as distinct as black and white. They fuse into each other and they overlap in many ways. Both will be relevant in the same problem situation. Let's discuss the formulation phase a little in a little more detail. This phase either involves formulation directly, or it may involve some preliminary formulation, which we call scoping. Scoping, I have written to Delemba to eliminate this from his new edition of the book. It's not a very useful concept, scoping. It says that instead of, in some situations, instead of carrying out a full-scale study, which will take a long time and will cost a lot of money, you may conduct a preliminary investigation to see whether a full-scale study is feasible or is desirable or not. This is called scoping. It is not implemented in all problem situations. You shouldn't take it as a necessary step, but it is possible. It may involve some preliminary scoping first. At the end of this scoping, a project proposal may be produced. The formulation requires full definitions of the narrow and the wider systems, as I said. You can make use of influence diagrams. Such a proposal should discuss whether a quantitative approach is feasible, whether data is available, whether the project is going to be cost effective. What does it mean? The project should not cost more than it produces, okay? It should be cost effective. And you should do this as honestly and as openly as possible. You should not make stupid promises that you cannot keep later on. You should point out all the difficulties and all the problems in your proposal. The modeling phase involves the hard aspects of OR, where you construct a mathematical model. What can you do is that if the situation fits a well-known structure, a structural approach can be followed in modeling. For example, using a known LP model for production planning. If the production situation is sort of a standard situation where a well-known LP formulation can be useful, you can follow this sort of modeling, or a dynamic programming model for equipment replacement, for example. For equipment replacement problems, dynamic programming is widely used. Otherwise, a process approach will be needed, meaning that the model has to be built from scratch. Actually, this is the more usual case. This is how you have to proceed, to construct the model from zero. An influence diagram can be constructed to help modeling. Here you make a choice of scales, obviously. If technical complexity is not very high, you can come down and construct a low-scale model, low-level scale model at a low level. Otherwise, a high level. If you go to the extreme, then your model becomes a black box, as we have seen. The model should have as many of the desirable properties of good models as possible. Most importantly, now this part is important, and you will have questions on this in the next exam. Please pay attention to this. Some of our friends are sleeping or talking. I don't know why you attend the classes. Huh? You don't attend the classes. It's a waste of your time for you, I think, for you. If you're going to sleep in the class, you can find a better way to sleep, a better place, right? Am I right? Okay, most importantly, the model must have internal validity. And there's an external validity, and you have to learn these, all right? What do you mean by internal validity? Meaning that the model is logically and mathematically correct and complete. Actually, when your instructors ask you in an examination, for example, to construct a model and then solve it, in a course in OR, for example, and then they grade your work, right? They grade your work according to internal validity. They check whether the model is mathematically and logically correct. That's what we mean by internal validity. Now, it should be tested logically and numerically and as early as possible. And then there is another type of validity of your model called external validity. Another term for this is generalizability. A model which is externally valid is said to be generalizable. You can generalize it to situations other than the narrow system of interest, perhaps. Meaning that the model must be representative of reality, that its findings must make sense in respect of applications. Ensuring external validity is difficult. Showing that the model does not have external validity is not difficult. Proving the opposite, that there is no external validity, is relatively easy, but showing that it is generalizable and it is externally valid is difficult. Now, these concepts of validity, and there's another concept related to this called reliability, are fundamental to all science. Not only to modeling in OR, but in all science, these concepts are important. They are important for research design. When you are doing research in any science, in any disciplinary science, you have to have a design of research. What sort of experiments are you going to conduct? What sort of hypotheses are you going to test, et cetera, et cetera. So these research designs, and in each experimental situation, you make measurements. So these are the fundamental tools of science, measurements, research designs. And attributes of these, the most important attributes of all these, are called validity and reliability of research, actually. So let's talk a little more about validity and reliability. I want you to understand these properly. Now, validity is about measuring what we want to measure. Suppose that you are measuring something. What sort of thing could this be? For example, you would like to determine whether smoking causes cancer. So you have to measure the effect of smoking in the formation of cancer, on the incidence of cancer, for example. This sort of measurement. Or measurement could be more simple. You might be trying to measure the distance from where you are sitting to the next wall. All right? Now, suppose I use a meter stick to measure the distance. Is this measurement valid? Does it have validity? If it has validity, then we will be sure that we are measuring what we want to measure. Now, if I use a tape measure, then I can reasonably be sure that I am measuring what I want to measure. There are no more alternatives. So the validity of measurement will be assured in this case. But suppose that I use such an instrument for measurement. There are such electronic instruments that take measurement. Maybe you have seen some. Huh? If I, by sending, for example, a beam of laser and measuring its reflection or something like that, it can take measurements. But now I'm not very sure about the reliability, the validity, because I'm not sure whether I am measuring what I want to measure. Maybe this is measuring something else. Suppose I conduct a survey. I put several questions to students to measure, for example, the level of satisfaction with this course. I put 10 questions, and you answer these questions, and then I have to evaluate those answers and translate them into a numerical measure of the degree of satisfaction or the level of learning, for example, that has been achieved in a course. You see, it is not easy to go from such answers to a final measure and be sure that you have actually measured what you wanted to measure. If I am, for example, interested in measuring the increase in knowledge that has been made possible by this course using answers that you have provided to several questions, then there is the possibility that maybe I am measuring the satisfaction level that you have obtained from this course, which is different from the level of knowledge obtained, or the level of enjoyment, let's say, or dissatisfaction. So there are such difficulties. So validity is about this. Let's make this more concrete. In experimental sciences, the internal validity of an experimental design ensures that an observed effect, suppose the effect we observe is a change in the variable y, delta y. For example, this is the increase in the incidence of cancer, delta y, is indeed the result of a certain cause, which is a change in another variable, x, delta x. For example, in the cancer example, what could this be? This could be the number of cigarettes smoked in Ankara, and this could be the number of cancer incidences diagnosed in Ankara, the change. So validity means we should be sure that the change in y is a result of a change in x and not as a result in the change in w or z or whatever, because you see y and x are related in a way, in this way. That is, the independent variable, this is cancer. Y is the number of cancer cases. X is the amount of cigarettes that have been smoked. W could be something else, because it's not only it's not only smoking that causes cancer. Diet can cause cancer, and there are many such independent variables. And the point is, we don't know how many variables we have here. Complexity tells us that the number of variables here is infinite. So how am I going to establish a relationship between cancer and smoking cigarettes? Right? This is the question. Okay, let's stop here.